Hey guys, this looks like a fun one. We're looking at a map of Russia and Africa, and across Russia looks way larger than across Africa, but it's actually a shorter distance. This is just showing how flat maps are flawed when your Earth is a globe. I kind of want to play around with this and see if I can do some math. First, let's go to Google Maps, and just to verify, yeah, Russia clearly looks larger than Africa. So let's go to this point right here. And if I click here, I can get the GPS coordinates. It'll be 22, negative 16.9. And then I can go over here and get these GPS coordinates. It'll be 11.6 and about 50.9. Let's go up here and get these GPS coordinates, 54.77 and 30.62. And let's go way over here. And these will be 66.06 and negative 169.92. So now we have GPS coordinates of each of these 4 points. Next, I want to try to put these on a globe. Let's go to Desmos and graph a globe. It's going to be x squared plus y squared plus z squared is equal to 1. This is a nice looking globe. Let's plot these points on this globe and see how they look relative to each other. I'm not sure how to plot GPS coordinates on a graph, so let's convert the GPS coordinates into rectangular coordinates. Here's the notes right here. In order to get the x value, it's r cosine of the latitude times cosine of the longitude. To get the y value, it's r times the cosine of the latitude times sine of the longitude. And to get the z value, it's r times the sine of the latitude. And the one I just graphed is a unit sphere, so we can actually change these notes to be about a unit sphere, which means all the r's are going to be equal to 1. The ones aren't doing anything, so we can smush it all together and we can use these simplified notes right here. Let's find the xyz of this one right here first. 54.77, 30.62. So now we can get the xyz. It'll be cosine of this, comma, cosine of this, sine of this, comma, sine of this one. And then after we plug all this into a calculator, we get these xyz coordinates. And we can update that up here. And now let's do the same thing for these coordinates. We can use these notes to get the x, y, and the z, and then we can plug it all into a calculator to get these decimal approximations. And we can update this point right here. Next, let's do this one, which will end up being this right here. And after we plug into a calculator, we get this right here. So this one is equal to that. And then we can do this one, which will end up being equal to this xyz. And here's the decimal approximation. And let's put it right here. Now let's plot these points on our graph. And here they are right here. So these two orange ones are the two Africa ones, and the two red ones are the two Russia ones. These two do look about the same as these two. In fact, these two look a little further. But on the flat map, these two clearly look further apart. So the map really distorts things a lot. Let's see if we can find the distance along Earth's surface from here to here and from here to here. Let's make sure that it's close to these numbers. So first we got to figure out what is the arc measure from here to here in degrees and the arc measure from here to here in degrees. In order to do that, we're going to have to use these notes right here, which is a three-dimensional dot product. The angle theta along the surface of the Earth is going to be cosine inverse of x1 times x2 plus y1 times y2 plus z1 times z2. So we're going to find theta1, which is the arc measure along the Earth's surface of these two, and let's call theta2 the measure of the arc along the surface of Earth between these two. So theta1 is going to equal cosine inverse of this times this plus this times this plus this times this. And then theta2 is going to equal cosine inverse of this times this, plus this times this, plus this times this. This times this is equal to 0.5456. This times this is equal to negative 0.2047. And this times this is equal to 0.0768. Down here, this times this is equal to this. This times this is equal to this. And this times this is equal to this. On both of these, let's smush everything together. And then we can do inside the parentheses, this minus this plus this is equal to 0.4177. And inside of this parentheses, this minus this plus this is equal to 0.5274. And we can use a calculator to get the cosine inverse of 0.4177. In degrees, it'll be 65.31 degrees. And we can do the same thing for the cosine inverse of 0.5274. In degrees, it will be 58.17. So in the place of theta1, let's plug in 65.31 degrees. And in the place of theta2, let's plug in 58.17 degrees. So right away, we can tell, even though this looks larger, it is a smaller arc along Earth's surface. This is 58 degrees and this is 65 degrees. And now let's verify these distances. Let's call this d sub 1 and this can be d sub 2. In order to find these distances, we're going to use these notes right here. It's the arc length on a sphere. The length is equal to the theta in degrees times pi times the radius, whole thing divided by 180. So to get d1, it'll be equal to the fraction of theta, which is equal to 65.31, pi, which is equal to pi, and the radius of Earth is about 6,378.1 kilometers. So we can plug that in right here. And all that is going to be divided by 180. Now we can do the same thing for d sub 2. For theta, we can plug in 58.17. For pi, we can plug in pi. And for the radius, we can do 6,378.1 kilometers. And that is all going to be divided by 180. Now, after we plug all this into a calculator, we end up with 7,270.2 kilometers. That is really close to what they said it was. And then for this one, after we plug all this into a calculator, we end up with 6,475.4 kilometers. That's also very close to what they said right here. Let's put in the number that we calculated, 6,475 kilometers, and let's update this one to be the 7,270 kilometers. So we just verified that on this flat map, the distances are very distorted. How exciting.